long today. That's all right. Chapel can go long every once in a while. That's fine. Especially if you're on the board of trustees. You can make chapel as long as you want. Just keep going. It's fine. Oh, today we learn a new topic, everyone. Parametric equations. Sydney, I remember you emailed me and then I forgot to respond. What was it about? I forgot. It was something about physics. I forgot. Did you typed it? It was, yes, yeah. Concave and convex. So there is a notion of a convex function. Here, let me add a page first. So you've learned about concave up and concave down. Here, let's let's go to convex, concave there. So let's see. Basically, they're both pretty similar in terms of the basic idea. They both have, like, if you were to turn this picture sideways, you would see that it's concave up. If you turn it 90 degrees to the left, and it's concave down if you turn it 90 degrees to the right. So basically, convex and concave things are kind of two sides of the same coin. So it's just a matter of where you're looking from ultimately. So there is a notion of something called a convex function, which is not really quite the same as concave up or concave down. There's, to the best of my knowledge, not the notion of a concave function, but a convex function is one that's essentially concave up. I mean, that's what it is. So I don't know why convex basically means concave up, but that's true. There's a more technical definition here that's better at understanding it, but yeah, that's that topic there. All right. So today I get to introduce a new thing, a new little topic called parametric equations. It's not on the syllabus, but you know what? We all got through material pretty quick here, so I might as well throw this in here. You'll notice though that when I insert these slides here, we have now gone from Calculus 1 material to officially Calculus 2. So hey, that's fun. Let me distribute this here. Last notebook, distribute page. All right. So what is a parametric equation and why are these useful? Oh wait, Sydney wrote something. Oh, thank you. Yes, you're welcome. So typically what we do is we think of plots, we think of just one function at a time, right? We have like typically a y is, for instance, equal to an f of x, right? So there's a function, you plug in x values, you get a y value out. So each x gives a unique y. But there are other types of functions you can make that are a little bit more sophisticated. Functions that are like this one. This is a function c of t. And c of t is not just a single number, but a pair of numbers. It's a weird function. You plug in a number and you get out a pair of numbers. That's the main difference here. And if we take a look at our example here, I have a function for us, a parametric function or a parametric equation as it's sometimes called. I have this thing c of t right here, and I can plug in basically the x coordinate is sine of, the first function here is sine of 4t, And the second function here is cosine of 3t. And as I was just sort of alluding to, if we want to display this parametric function or parametric equation, what we do is we plug in for different values of t, and what we get out of it are different x and y coordinates. So here, I've plotted the point C of 0. So what happens if I plug 0 in for t? Well, if my t is 0, my sine will be 0, and my cosine will be 1. So I'm right at this point 1, 0. If I plug in 0.3, you can see the point I get is right there. And if I plug in additional values, I can get a point here, a point there, a point there, and a point there. It's kind of fun to plot these on Desmos and to show you how to plot it on Desmos. So let me go over how to do that. You can also plot them on your TI calculator, but I'm probably not going to go over that. So let's enter in this exact parametric equation here. So I'm going to enter in C of t, and I'll have sine of 4t and cosine of 3t. And will it let me do that? Of course not. Let's just do this. There we go. That's better. All right. Didn't like the C of t there. And so you can see I get the same sort of shape here. Let me make the picture bigger. Right there. And I can change on Desmos how far this goes. Like I could have it go out to 3. Yeah, you want to see it? It's pretty cool. Here, you know what's really fun to do is to make a constant b for the endpoint and then just make a little slider here. And we'll make that 0. We'll make this like 10. There we go. And then as I move my slider, I can let it trace out this shape. Isn't that kind of neat? Yeah, and for real fun, you can like press the play button, let it do its thing. And it just retraces itself over and over again. So yeah, this is pretty fun for making interesting shapes. You can sort of see how this is kind of cool in a way. I like it. So parametric equations are really useful for describing, for one thing, particles that are moving around. So this is pretty key in physics, right? In physics, you have particles moving about and you want to be able to describe them. This is also pretty important for computer graphics. In video games and other things, you often have an object flying around in 2D plane or maybe a 3D space. How do you represent that? Well, you use parametric equations. So it's actually a pretty useful idea. So okay, that's a picture of parametric equations. All right, let's go over some terminology here. The curve produced by plotting a parametric equation is called a parametric curve. We usually just call them curves though, but yeah, parametric's fine as well. The input variable for a parametric equation is called a parameter. That's why we call them parametric equations, because they have parameters. As I already mentioned, the first term here in this C of t gives the x coordinate, while g of t gives the y coordinate. And because of this, it's also very common to write down parametric equations this way. To just say, oh, my x coordinate is given by this and my y coordinate is given by that. Now, what's interesting about parametric curves is that they do not pass the vertical line test. So if we go and we take a look at the example I just did, you can see, yeah, it definitely does not pass the vertical line test. But still, it's a function of the parameter t. You give inputs t, it's just you get outputs that are pairs of numbers. So still function-ish, just not the type of functions we normally think about. Now, one of the things we need to be able to do is figure out parametric equations for things we want to be able to parameterize, right? That's a pretty basic task. How do you parameterize things? And so to do that, we're going to go through a few common parameterizations. These show up all the time in applications. First, we're going to discuss how to give a parametric equation for a line. And then we'll also discuss how to give a parametric equation of a circle. And believe it or not, that describes a lot of cool things already, because you can combine circles into each other and lines into circles. It gets pretty cool. So let's do an example or two of this. All right. Examples. And just example. All right. Give a parametric equation for the line through the point, states the point 2, 3, with a slope of m equals, I don't know, let's say 1. 1.5. 1.5. Now, we know how to do this the old-fashioned way. The old-fashioned way is to use the point slope formula. Right? So the old-fashioned way is basically, oh, y is going to be equal to m times x minus a plus b. Do you remember doing this? And I'd plug in what my slope is, and then I'd plug in what my a is, which is 2, and my b is 3, and I'd get that nice, that would give me the equation of my line. And this is great, but there's a problem. It's not parametric. Not a parametric equation. Remember, a parametric equation will have a t in it, and I'll have a parameter t. This one does not have a t in it. So this is kind of the wrong answer. So how do we get the parametric equation of a line? Well, let's take a look at our theorem here. We're going to look at part A. It says if you want the line through the point AB with slope m, what you ought to do is write m as a fraction, s over r. So let's begin by doing that. How can I write m, my slope of 1.5, as a fraction? Yeah, first thing to notice is I can write m is 3 over 2. And so in our theorem, that means our s is equal to 3 and r is equal to 2. And so we have 3 divided by 2, or 1.5 right there. And so that's our s and our r. And of course, we want it through the point 2, 3. And so that means our a is 2 and our b is 3. And so thus, we want our parametric equation, C of t, we literally just plug in. And so it says take a plus r times t. Uh-oh. Suspected spam caller. No, I accidentally answered a phone call the other day, and it was from a friend from college who I hadn't spoken to in like 16 years. And it was really sad because I eventually figured out that she was stuck in a mental institution. And yeah, not good. Not good. I tried to convince her I was not a computer. I'm not sure if I was able to really do that. But yeah, anyways, that's what happened last time I answered the call and I didn't recognize the number. Yeah. I've been trying to get in touch to make sure with people who know her better. I'm like, is everything okay with her? Yeah, these things happen. The older you get, the more you run into this stuff. All right, so B is 3 and my S is also 3 plus 3t. Right there. There we go. That's it. Or if you like a different way of writing it, or you can write it this way. X is equal to 2 plus 2t and y is equal to 3 plus 3t. Though if you're going to plot this on Desmos, it's going to want this version here, okay? It's not going to like the other option. So let's take a look. First, let's plot the original old-fashioned approach. Well, we'll just do that. So that's 1.5. Y is equal to 1.5 x minus 2 plus 3. So that's the line. That's the line with slope 1.5 through there. And now let's do the parametric version. Parametric version was 2 plus 2t, and then a 3 plus 3t. And is anyone seeing anything? I don't see. Oh, it's very hard to see because purple and blue kind of blend together, right? Let's there. There, you can see it better now here. I'll make this a dashed, make it that there. Now it's easier. There, do you see it? It's right there. So you can see how it's sort of giving that line segment there. But it doesn't give the whole thing, does it? Like you have to sort of adjust your value for t. Like so -1 will get it to go backwards. If I increase it there, if I do a 2 there, it goes further that way. Sometimes it's really fun to do something like the following on Desmos. You replace this with a U, replace that with a U and add a slider for U right there. And what you can get is a point that sort of traces out this curve. So you can go here and get your little slider and go like that. That's pretty neat, huh? Okay. Well, a line is fun. Yes, there are fun ones. There are fun ones. Do you want to see one of my fun ones? I mean, yeah. You're like, I showed you the rolling ellipse last time. That's basically the fun one. I mean, I got lots of weird. I had a rolling hyperbola at one point. Yeah, rolling hyperbola. I don't know if we ever finished this one. This was the next one my student wanted to know about. Right now, there's too many things. It's too hard to follow. Too hard to follow. The rolling ellipse is the winner, if you ask me. That one is the rolling ellipse. It's hard to beat that one. There it goes. Yeah, but do you see? There's the equation for it all right there. Yeah, it goes on for a while. And if you pay close attention, you'll be like, what's Q? Well, Q is defined way down here somewhere. And so like all those have different equations. Yeah, it's not easy. It's pretty non-trivial to do that one. But we could do other things that are fun. Okay. So that's one approach. What are the other types of lines we may be given? This one comes up all the time in multivariate calculus. You've got 2 points, a point P and a point Q, and you want to parameterize the line between them. How do you do that? Let's just take a picture of this. We'll do an example. It's actually pretty straightforward. So we'll do this one in orange here, example. Gotta spell the word example correctly. Oh man, look at this thing. This thing is enormous. It really is kind of like just a plug in and go type setup. Okay. Let's say we're asked to find a parametric equation for the line segment from, let's say, -1, -2, and 2, 4. All right, you want to just parameterize that line segment, not the whole line, but just the line. How do you do that? Well, it's pretty nice. You let this be your A, you let this be your B. This is your point P. C and D right there. And so the formula gives it away for you. All right, it'll be a -1 plus t times my c, 2 minus a -1. And then I'll have -2 plus t times 4 minus -2. That's awful looking. And if I multiply through here, I'll get -1 plus, well, what will this be? This will be a 2 minus, this will be a 3t. And this will be a -2 plus 4 minus plus a 6t. That's it. And we could check that this worked on Desmos. We can just, oh, and I should mention this is only for t that's in the interval from 0 to 1. So if you go from 0 to 1, you'll start off at the point P and then finish at the point Q. So let's plot this. We'll leave the rolling ellipse there for later. Oh yeah, it doesn't like that. So we have -1 plus 3t and -2 plus 6t right there. And it does it from 0 to 1 for me automatically. And you can see I'm right there at that point, -1, -2, and at 2, 4. Does it perfectly. All right. That's the basic idea there behind lines. And one final one is circles. Let's suppose you want a circle of radius r centered at the origin. That's got to be right at the origin, right there. Okay, how do you do that? Well, it's just r times cosine t, r sine t, with t between 0 and 2 pi. So we'll do one more example. We'll give a parametric equation of a circle of radius 5 centered at the origin. And really it's pretty straightforward. The equation is c of t is, my radius is 5, so 5 cosine t, 5 sine t, and t goes from 0 to 2 pi. That's it. That's it. I'm literally copying this equation exactly. Oh, technically I don't include 2 pi. That's all right if you include 2 pi as an endpoint. That's all right. So let's plot this one. It's be 5 cosine t, 5 sine t. Doesn't look like a circle yet. Looks like just an arc, but I type in my 2 pi and bam, there it is. It's pretty nice. Okay. So this is a good one to use Desmos for. I just sort of realized many of you may not have brought a laptop though. So those of you who do have laptops, feel free to jump ahead and do these. But if you don't have a laptop, you can do parametric equations on your TI calculator. It's kind of neat. Let me see if I can remember how this works. I think I go up, do I go up to plot? No, that's not it. Where is this thing? It's been a long time. I go to, is it mode? Mode. I have a feeling this is not, yeah, this is where I go. Here it is. Do you see that? I don't know if you can see it very well. Here, let me get the, yeah, that's it. Yeah, here's the magnifier so we can all see it. Okay. There we go. I can click right there. And now I'm in parametric mode. And I go down and I press enter. Right there. Enter. I'll go back up. It's been selected. Now I press y equals. And what I have is a x and a y now. So if I wanted to plot that circle, I could do 5. Here, I'm gonna have to get out of magnifier mode here. No, I don't know how to get out of it. Oh, there it is. Here, I'm gonna have to close it. I'll do 5 times cosine. And then if you press this X button, guess what? It's now a T. It changes. I'll press enter. 5 times, I can do sine and the variable button, T. Then I can go to graph, and my window is really messed up. So let me go to window. I have to give a T min and a T max. Somehow my calculator knows the T min is 0 and the T max is that. But I also have to give an X min and an X max. I think negative 7 is good there. Negative 7 here is good. Press, now let's graph it. There we go. Now you might say to yourself, that's not a circle. Well, it doesn't look right, does it? It looks like an ellipse. If we wanted to fix it, we could go to zoom here. And I think we just do go down to Z square. There we go. Now that's a circle, my friends, very roughly. Z square makes it so that it's the same distance on the axes. All right, so if you want to test your answers, you can now. So I'll leave these problems up here, and I'll copy and paste some equations next to them in case you don't have those handy. And we'll just use this stuff. They start off easy, and then I start asking you to do weird things. I get a little carried away. Like, you know, it'd be fun if they could do this. There we go. So now I have up on the screen the equations and things along with the problems. Oh, you're using your
Because when I graph it, I get that.
let's look at your y equals. Well, you know what it is? It's not a real TI calculator. That's what it is. Probably that's what the problem is. You got a bootleg TI calculator, not the legit one. I know it says it does, right? Somebody just never bothered to program it all. They're like, just make it look like it works. That's all we need. How's it going? Oh yeah, very good. You're onto it. You get something? Yeah. Oh wow, you did a lot of them. Yeah. Yeah, that's right. Yeah, that's right. Oh, good job. How's it going?
Not that 10% wrong.
Just don't do the C of T equals.
Ah.
For some reason, it just doesn't like that. There. And now it's maybe we got it's a Mac. Macs have got to get on this touchscreen thing. Figure I don't
Well, that's
know.
what I for.
That's what I know that's their thought process, but I don't
mean-
see it anywhere. Well, you gotta go up further. It's at -4.9.
Oh.
So
Oh, when I go down, then
well, there we go. There it is.
Oh.
Yeah, that's alive. It worked. How's it going, Josh? Yeah, that's it for part A. And for part B, I think that's basically right. Uh yeah, well, I have to look at the equation really. I don't know what this is.
something negative.
Oh, good. Oh, I see. Yeah, yes, indeed it is. Yeah, that's correct. That's correct. How's it going, Keelan?
Good.
All right.
Yep.
Yeah, yeah. I think the only thing that might be tripping you up is you need a plus there instead of a multiply.
That is a plus.
It is.
Yeah,
Is it really? Okay, because it looks like a dot to me. Okay. All right, all right. How's it going? Oh, good. Yeah, you did it. Yeah. Yeah, the first four are relatively, you can figure it out based upon what I've told you so far. Part E through I requires you to start getting creative. Oh, you figured out that one. Very good. Yeah, I think it should be an 8. Yeah, that's fine too. I like it. I like your answer. You're like, I'll do 16/2. That's correct as well. 16/2 is 8. 8/1 is 8. 4/1/2 is 8. All of those. All those are 8. It's interesting to sort of think what the difference is, though. There is a difference. Does anyone have any ideas on how we do part C?
You just
Yeah, we can make a point. Yeah, what's the point that this line goes through? There's lots of them. 0, 9, yeah. Just plug x equals 0 in, you get y equals 9. And what's the slope of this line? -4. There. You can extract that information from it. I think you'll need pieces of paper eventually, Megan. We can't just do it all in our head. I mean, some people can, but not me. How's it going?
That's a plus, by the way.
Yeah, I can actually tell that one is, and I lost the sheet. So I gotta find the correct sheet here. Yeah, that's it. Good job. Good job. Yeah, start with equations of lines. I know they're not the most interesting, but eventually I'll have you find the equation of a cycloid, which will be pretty crazy. How's it going, Zach? I agree. It's good. Good job. Sometimes said to myself, it'd be fun to do a course on this type of content, but with the goal of making 3D graphic software. You know, that'd be pretty fun. Yeah, that's it. Yeah, we're doing good there. Yeah, okay. And if you get through all of these, just know that you can keep going. I just can't show them all on the screen. But there is number 2 and number 3, which is like, I want you to figure out how to parameterize that purple line, which is what you get if you're a bug stuck on a wheel that's rotating. You're keeping track where the bug is. Right. That's pretty fun. I like that. I like that problem. And if you're really hardcore, you could try making an animation of it in Desmos, you know, the moving. That's what I did with the rolling ellipse. The rolling ellipse was like a kind of version of that. Uh, how's it going, April? Yeah, you figured out part E, very good. And part F, let me look. Yeah, that's right. Very good. That one's tricky, I thought. Part G, yeah, you did it. Almost. I have a plus, I have this T plus 3 squared. And you do not, so. the idea here is that if my x is t plus 3, right? Then my y, it's got to be the square of that. Yeah.
So 100 plus 9. Oh, I got it.
It'll work. If I plug t equals 0 into this, I get 3 and I get 9 here.
Oh.
Yeah. Yeah, no, you're on the path to enlightenment, Zach. Keep going. That 2 is exactly what I want to see. Or, well, not exactly what I want to see, but it's close, it's close. The other advantage of getting a real TI calculator is you don't have ads. Looks like an ad right there at the top. $4 off McDonald's app. It looks like a calculator / advertisement. Very good, yeah. So shall we talk about part E a little bit? Part E is mean. Part E says give a circle of radius 2, but it's no longer centered at the origin, it's centered at 1, 2. So how do we think about that? It'd be nice if it were centered at the origin, right? That'd be easy. Because then it would just be 2 cosine t and a 2 sine t. But it's not there. That's not. Yeah, how do we make this thing? How do we sort of pick up this circle that's at the origin and move it so that it's centered at 1, 2? Yeah, Zach. No, not quite. You will get a circle, but it won't be at the right spot. I'll tell you. You add 1, the 0.12. You're like, oh, I need to shift 0, 0 to the 0.12. I'll just add 1, 2 to it. And when you do that and you add these, so you'll do this term plus that, so you'll get a 1 plus 2 cosine t, and then a 2 plus 2 sine t. Isn't that sneaky? So basically, if you have something that's normally at the origin and you want it somewhere else, like at 1, 2, you just add 1, 2. By the way, this is something that I'm showing here that I haven't really described. This is called vector addition. If you've ever seen vector addition before, that's essentially what I'm doing. So we can plot this. Let's plot it. So 1 plus cosine, or 2 cosine t, and 2 plus 2 sine t, go from 0 to 2 pi. There it is, and the center's right there, right at 1, 2. So it all works out. It's a little tricky at first, a little tricky to see how to do that. All right, part F. Part F is kind of similar to part C, isn't it? Very similar. But it throws in a little bit more into it, doesn't it? It says, I want C of 0 to be 2, 2. See if you can figure out how to parameterize it so that that happens. Yeah, it's possible. It's possible. And then G is weird because it asks you to parameterize a parabola. Much harder. Still doable. How's it going? So many challenge problems, huh? So for F, you have the equation of the line. So what's the slope of that line in F? What's its slope? Geez, I don't know either. I was hoping you guys did. Does anyone know what the slope of the line is? Part F. 3, right? It's the coefficient of X. And now we need to have a point. 0, -4 is the point it goes through, yeah. What's another point that we know it goes through? 2, 2. So which one do you think we should use for our P, for our point AB? The 2, 2 is a good choice because if you plug T equals 0 in to this equation, so right here in this equation, if you plug 0 in, what do you get? You get A, B. And so if you want to make sure that your C of 0 is 2, 2, you better make sure that your A is 2 and your B is 2. And then it all works out. What's that? Ah, G. Yeah, G is tricky. G is tricky. Because I never gave a parabola before. I haven't told you how to do parabola. I just kind of throw it at you.
Was that the end for F?
What was it?
Was that the end for F is making the point?
Yeah,
That's it.
that's the hit. Yeah, that's it. That's all there is to it, really. For G, it's a lot harder because you have a parabola. Not a line anymore. Takes a lot more thinking. It's a good puzzle. Yep.
For this one, because we have 2 points, we don't use that equation.
Which problem are you working on?
F.
F?
Yeah,
Yeah.
can we do that?
So there are 2 equations for lines. One is for when you have 2 points given, P and Q, and another for when you have a point and a slope given. And I think it's easiest to do this part F with this one. But you could do it with that one too. Yeah, either one works. Just one's a little bit easier if you ask me. There will be a squared T somewhere, yeah. I want to let you guys think about it a little bit more before I delve into the details. Yeah, it's not a bad idea. Not a bad idea. All right, I can tell you, you're probably like, Brandon, how am I supposed to do G? You never told me how to do it for parabolas. I don't know. Sometimes I just want to see if people figure it out independently. Kind of like a little experiment, you know. Here, let's try this. Free form. taking a picture of this. See how well this works. Right there, okay. All right, let's do these last few problems here. What the? Man. There we go. I don't know what happened there. All right, so for part G, we have a problem. The problem is we want to parameterize this parabola. Now, I can find a kind of dumb way of doing it. That's not that sophisticated. Do you want to see my dumb solution? It's also wrong. So, wrong. Just so we're clear, okay, this part's wrong. Here's what I can do. I can let x equal t, and if x is equal to t, then since y is equal to x squared, then y is equal to t squared, and so I can just let my c of t be t squared. And that'll give me a parabola. You want to see it in action? Yeah, let's see it in action. All right, so here I got t squared right there. Well, we'll make a little slider here so you can see my, see, it's very parabolic-y. And if I do like say -2 there, it can, and go backwards to there and all that. See, it is a parabola. So I don't know if there's a name for this, but it's basically let x equal t and let y be whatever you get when you replace x with t. I like that one. There's just one issue with this. Does anyone see why this is wrong? There's something wrong about it. It does. C of 0 is 0, 0. Okay, so this is bad. All right, does anyone have any, how could we fix that? All right, add the numbers. Okay, that's a good idea. All right, so we will try also wrong, but not a bad idea, which is why don't we just take this t squared, and before when we were working with circles, Brandon, right, you were like, just add 1, 2. So I'll just add 3, 9 now. There, I'll just add 3, 9. It kind of makes sense. It's like, yeah, why not? Okay, well, let's see, why not? No, it's still a parabola. So I got t plus 3 here and t squared plus 9. There we go. There we go. There it is. It's a parabola, all right. There's just one problem. It's not the parabola I want. I wanted this one. I wanted to go along this parabola, not that one. Ah. So yes, I got a parabola here, and if I plug in 0, I get the 0.39. Great. The 0.39, in case you're wondering, is well, right about where you probably suspect it is, right where those two parabolas cross. Right about there. The only problem is it's not really the right parabola. So okay, so how do I fix this? All right, this is kind of a dirty trick. Here's what you do. What you do is you let x equal t plus 3. Why do you do that? Because the idea is that if you plug in t equals 0 into here, you'll get 3. That's good. And then what's your y going to be? Well, your y is x squared. So it'll be t plus 3, all squared, which is, interestingly, not t squared plus 9. It's t squared plus 6t plus 9. And so now we get our c of t. t plus 3, t squared plus 6t plus 9. So this is the dirty rotten trick. This is the trick. You say, oh, let me just worry about getting the x to give the correct value first. So I'll do t and then I'll add 3 to that. And then my y will be determined fully by this. And so now let's fix it. It's easy. I just add a 6t here and there. Now it's all good. Might be a little hard to see there, but it's on the correct thing. If I plug in 0, I get the 0.39. It's all set. All right, so that was part G. Very tricky problem. All right, part H. Let's look at part H here. It says we have a circle of radius 1 centered at the origin. Okay. So let's begin with a wrong answer to that one. Yeah, I hope you notice a pattern with these, okay? In most math problems, you're like, I should only get the right answer to begin with. You know, I should only right answers to start with. But with parametric equations, doing it wrong, it can be really helpful as long as you realize it's wrong, okay? Doing it wrong when you don't realize it's wrong, not as helpful. All right, so let's do it the wrong way. The wrong way is to just use the equation we got, right? It's that r times cosine t sine t. So let me do that. I'll do cosine t sine t right there. All right, so that looks pretty good. If I were to hop on Desmos real quick and type this all in, I have cosine t sine t right there. Yeah, looks pretty nice right there. Maybe I'll stick a b here, add a slider. You can sort of see how here. Let's change this from 0 to 2 pi. There we go, and we can kind of watch it fill in the circle there. It's very satisfying, isn't it? Nice circle. Much better looking than the TI circle. Let me say that. That looks like a glorified polygon. All right. So that's a nice looking solution. Now, what's wrong with it? Well, the center's fine. It's centered at the origin. C of 0 is, well, what is C of 0 anyways? 1, 0. Oh no. I'm not supposed to get that. I'm supposed to get 0, -1 where it starts. Ah. Okay, so here's our problem. We're starting at 1, 0 right there. And we really want to start at -1, 0. Or 0, -1. That's a bummer. That's a real bummer right there. A couple different ways you could try fixing this. Notice what happens. What happens if I go and pick a negative endpoint here for my parameters on -1? See what happens there? Kind of, if I start at -1, it's like I'm going backwards a little bit. You know, -2, I go backwards a little too far. Well, what's the right value here to make sure at least my curve starts there? Pi over 2, says Jackson, and he's right. Jerry might have said it too, I don't know. No, you didn't? Okay, all right. So this is kind of nice in that it's like, well, we get the right answer if instead of, you know, here's sort of what we see. Observation. Oh, I don't want to write in highlighter, so make an observation. Observation. C of -pi over 2 is 0, -1. Okay, good observation there. So now the question is, can we use this observation to get this first thing figured out? See if we can do that. Does anyone have any ideas? How can I mangle my C of t? to get it so that instead of C of 0 being 1, 0, how can I make it so that I get this thing instead? Next try. It's like what I want is when I plug t equals 0 in, I want negative pi over 2 to be plugged into my cosine and sine, right? That's kind of like what I really want. It's like I want it that when my t is 0, what gets plugged into here is negative pi over 2 and negative pi over 2 there. Anyone think of a way to make that happen? I'll let you think as I fill in more stuff. So it's like, man, it'd be really nice if this were just a little different. There we go. It gives me 0, negative 1. How do I make my C of t work so that when I plug in 0, I get this stuff? I want to change my C of t so that when t is 0, bam, out comes this thingy. It's hard to see. Hard to see.
T plus, T minus.
Yes. Lee is like, hey, didn't we do something where we changed the t here, right? Like we like added 3 to the t. Why don't we subtract pi over 2 from the t? So yeah, let's try that out. So everywhere we see a t, we replace it with a t minus pi over 2. Aha. Let's try this one out. You want to see if it works? Yeah, let's do it. So I'll go to here and I'll just do minus pi over 2 and get something crazy looking. Pi over 2 there. I'll let my b go from 0 to 2 pi right there. Very good. What happens when I plug in 0? Uh-oh. Oh, wait, that's because I changed this. 0. There we go. There. From 0 to b, yeah, it's working. It's going perfect. Everything is going precisely as planned. So now the circle is starting negative pi over 2 radians instead of right there. Okay, that's good to know. Okay, now there's this other criteria there for H, right? The other criteria is that C of pi over 2 is going to give us the 0.10. Does that work? Yeah, let's check. Yeah, we lucked into it, folks. In this case, we can see that, yeah, if we do cosine of pi over 2 minus pi over 2 and a sine of pi over 2 minus pi over 2, yeah, we'll get the 0.10. So this works. That means this is correct. We found the appropriate parametrization of that circle. Now here's an even harder one to think about, and we'll finish up with this one, I guess, next class. But you could try thinking about it in the interim. You got a circle of radius 1, and now it's centered at 0, 1. And you want C of 0 to give the origin and C of pi over 2 to give negative 1, 1. So, oh man, this is getting harder, But I bet you some of you could figure it out. I bet you could. It's not as hard as it looks. It just looks kind of hard. So as you can tell, parametric equations, they're kind of tricky figuring out how to set them up at first. But they're pretty cool. One thing to mention is if you're into computers in math, when we do parametric equations, we set it up like this, like, you know, you have x here, x here, and y there. On a computer, when you're doing computer graphics, y goes down like that and x goes this way. Yeah, and so it gets a little confusing. So be aware if you do computer graphics, the setup is different. All right, that's it for today. Any questions, online students? Okay, I'll see you on Wednesday. Bye.